previously declared? Good question. All right, so that was bottles. Let's take a look now at two buggy programs just to see whether this starts to pop out a little more. This is buggy4.c. So this is a program that's supposed to increment a variable, but I claim does not. All I've omitted at the top is the comments. So let's look at the top. At the top, we have a function prototype for a function that's apparently called increment that takes no arguments and returns nothing. Main does what? All right, so x gets 1. It prints out the value, just says ... calls increment, then prints out the value of x again. So this is buggy. This is not, in fact, going to increment x, but y. Let's look at the increment function. This is broken, and in fact won't even compile. Why? Yeah, it doesn't declare the type of what? OK, so it hasn't declared a type for the variable x. OK, I'll fix that. Let me do int x. Better? So not quite. This, too, is now actually worse. You can't declare a variable like this and then do plus plus. Frankly, it doesn't even have a value yet. So that's not quite right. So it's a good thought, and it is related to the fundamental problem here. Yeah? Yeah, exactly. So x exists, but it only exists up here. So it only exists in the scope of main, whose scope is defined by its own curly braces. So OK, all right, let me fix. Then let me do this. Now increment has its own x. OK, yeah?
Increment is not taking input from the main function.
OK.
So x, and because first x is declared in the scope of main, then that x has no value. So you need to say that increment int, instead of void, we should say int whatever. I guess x is going to be.
OK. OK, so we somehow need to pass from main the value of x into this increment function if it's actually going to do anything, if I can simplify. And let me just, before I erase this second mistake here, would this compile, though? So this would actually compile, right? Because if you go back to basic definitions, what is increment now doing? Well, it's not taking any input, but that's fine. It is declaring a variable called x, and it's of type int. And that means what? 32 bits are being set aside inside of increment's frame. Remember when we drew RAM as a big rectangle? So a sliver of RAM has now been allocated to the increment function. And in there is some 32 bits that are going to be used for this variable x. And then it's incrementing x. But there is a problem here. What is x at that point in the story? Like, we don't know. And in fact, if you think back now to last week's picture, when we drew RAM as a big rectangle, the interesting thing about this design of memory use in a computer is if this is main at the bottom, well, main is kind of lucky in that his memory always sticks around until the program ends because his gets put into the computer's memory first. Well, what if you call a function foo? It ends up there, but then foo returns. So what happens to it? This gets reclaimed. What if you then call a function bar? Well, it might go there on top of main, but then it returns, so its memory goes away. But it doesn't really go away per se. It's just that the computer forgets that those bits were once used by a function foo, or those bits were once used by a function bar, but all those zeros and ones are still there. All the magnetic particles or all the electrons are still there in the same orientation you left them. And so what might happen when a function like increment is called? Well, increment is going to get a sliver of memory here. But if you had 0, 1, 1, 0, 1, 1, whatever the zeros and ones were, when a function called foo or bar was using that chunk of memory, what value is going to be in x at this point in the story? Right, the answer before was this, but really it's whatever junk was left over there by those previous function calls, foo or bar. So this, too, is going to be, for bad guys, an opportunity to do bad things, right? If you can imagine a program whose purpose in life is not to increment numbers, but to ask you for your password, right? And you guys have been doing this. The Submit 50 program, for instance, in the appliance, asks you for a password. Well, that password gets stored in the appliance's RAM inside of some function, inside of some slice of RAM allocated to some function. But as soon as you're done running Submit 50, OK, that memory is given back to the operating system, and these slivers go away. But what about the zeros and ones? What about the ASCII characters that were temporarily in RAM storing your password? Where are they? They're still in RAM, right? The computer's forgotten where they are, but if a bad guy has physical access to your computer or somehow hacks in via some network connection and has the ability and the savvy to poke around your computer's RAM, you might see 1, 2, 3, 4, 5, or whatever your password is, just lying around there in memory. And it's simply because, again, computers' use of RAM is this simplistic. So what's happening here? I'm saying give me 32 bits, call it x, increment that value, but who knows what that value is? Maybe it is 1, 2, 3, 4, 5. So what did I just do? I plussed it to 1, 2, 3, 4, 6. But then this function returns. And so what effect does this have ultimately on this variable here, x? Absolutely none. It's in a completely different sliver of RAM. So that was a lot. Why don't we go ahead and take our 5-minute break here. All right.